All right. Good morning, everyone. Good morning, everyone. 2 minutes till afternoon. My name is Brandon Trotter, and I had the pleasure of working with 2D materials, most specifically biosensing using quasi-epitaxial graphene with Professor Kevin Daniels back there. Thank you very much. So this is our background, everything we're running through today. And to actually get into it, we were all there during 2020, during the coronavirus pandemic. And one of the big problems with the COVID pandemic outside of dying was that the testing methods that we had to detect the virus were lacking. There were two main ways you could test for the virus. There was PCR testing, polymerase chain reactions, which were those nasal swab tests you took that took a couple of hours to get back. Big problem with those is that, one, they took a long time, and two, they needed extensive lab materials and extensively trained teams. When you have thousands of people who are all getting tested for something, that 3-hour wait list there is going to get extended to way longer than that. And places that don't have proper infrastructure, since it was a global pandemic, can't really use PCR testing. And then we have the rapid tests. Rapid tests were great, and we all thought they were our savior, but the big problem with rapid tests, even though you got back a quick response and a quick diagnosis, many times they were not properly the right diagnosis. Many times you got a false negative or a false positive, so you had the worst of both worlds. Something that was either too finicky and slow, or something that was fast and had a high chance of being wrong. And that raises us to our next question. Is it possible to detect these pathogens in real time and to overcome the current limitation of these sensors? That's where our project comes in. The previous sensor that we had was highly selective. First off, you could find the virus in 1 ultragram per microliter of COVID samples and only 60 copies per milliliter in order to find the virus. Second, we could find through multiple different avenues, such as saliva, nasal swab, and aerosol-based samples, which I mean our breath samples, am I correct? And the way this works is we use a Internet of Things sample from saliva and breath-based samples. Now, quasi-epitaxial quasi-freestanding bilayer epitaxial graphene can detect the virus itself, but it cannot detect the viral load, which is something we've been working on. In order to get the viral load and the progression of the illness, you need two things, which is first the neutralizing antibodies and the viral load. You put those two together, and that's how you get a graph of the illness. We can track how far someone is, how infected they are, how long ago they got the virus. And using these two factors, the viral load and neutralizing antibodies, we can then determine how sick someone is. That's what we've been working on over the summer. So what is quasi-epitaxial graphene? I'll call it QEG for short. Well, first off, quasi-epitaxial bilayer graphene. Graphene by itself is an epitaxial structure. That's that honeycomb lattice that you hear. But usually it's only one layer, and it's just one layer of carbon atoms. With bilayer graphene, we have 2 layers of carbon kind of smushed together, very close to each other, and then it's supported by the silicon carbide structure. That's where the quasi-freestanding part comes from. What the problem with normal graphene is that it's highly selective and it reacts to pretty much everything. So when we run testing on it, it doesn't really select and tell what the virus is. But through here with quasi-QEG, we're able to find the virus a lot better. What we make it is by putting under a lot of pressure. We see where it's formed, where we cool the silicon to 1050 C under 150 standard liters a minute and 9 mbar of hydrogen, and we passivate that with argon afterwards. And this is a structure of bilayer graphene. So you have the 2 layers of graphene here. You have the substrate, which is this block that it sits on, and that's how we get a more sensitive and more effective graphene. So this is what I did during the summer. First off, in order to get the sensor, we get our graphene, and then we do a process that's called etching. Etching, it sounds complicated, but I'll explain to you very simple. First, we take our sensor, we want to cover it with copper foil. The copper foil, then you go about 0.5 millimeter on each side exposed. From then, we do etching, kind of rip off the edge of the graphene, and that's not covered, it's then taken off. Then our sensor goes to here, where we have the graphene at the top, and then we have the substrate at the bottom, the exposed center. And in order to actually do the testing and have a conductive layer, you put these little metal contacts, which are titanium and gold. In total, they're 200 nanometers thick. About 15 nanometers are the titanium, and the other 185 are gold. And from there, we run our micro manipulators through it, and run a constant current through it. That's where we're going to do our testing. Here's the copper foil we use, and then here's our finished sensors. The copper foil ones is a little torn up. And this is how it looks at the end of it. From there, you have to do our coding process. And currently, our coding process is kind of one of the harder parts of the project, just how long it took. You have to come in during the night and coat for about a 14-hour window. So if we wanted to get started working in about noon or 10 o'clock the next day, they'd come in at like 8 p.m. the day before, so 14 hours to pass. So what we do, come in, we code with polylysine, which polylysine is a buffer solution that does not mess with the conductivity and the conduction path and the pi bonds of the materials. It bonds covalently to the biomarker and non-covalently to the QEG. So there's no disruption, it doesn't mess with anything else. What we do, we come in, code the sensor, then we have to refrigerate it for about -3 degrees for 14 hours, and then we come back and we have about 4 hours during the day to work with it and do testing, just in sort of like its most optimal state. And then using 1 microgram per milliliter was how we used to check antibody binding events. So here's what we got our results. So when we did our last testing, we didn't really get the results that we really wanted. You see here, we first started off, the graph is going up. These first movements here, because with the bench movement, was when we ran our current through, we saw a little spike based on that, see the table physically moving. And then we actually started the actual conduction itself. We got a negative graph, which we did not want. That's very unusual when we do our actual coding and run a sample through it, and things start reacting, plus get coming positive. So we were kind of confusing that. Eventually, we added 1 ultragram per milliliter, and that's when we got that negative change. And then when we changed 100 nanograms per milliliter, that's when we're back into this positive range. So we've determined that our current sensor responsibility is much lower than we initially expected and we hoped for. But I mean, part of science is making mistakes and learning from it. So this is a very ongoing process. It's more of a furthering the capabilities process rather than like going for a specific result, that's expected at the end. And the different biosensors introduce different sensing mechanisms. And this is an up-close atomic force microscopy, which is basically, it allows us to see, like if you saw Theo's project, he had these little pictures of him. And it allows us to see the surface of very, very tiny materials. So the 2D material is a very small material. It's basically like an alpha size. So this shows a sparse coding. And one possible problem is that the last strain was different than the antigen sensor. And so the next steps are to track a new antigen spike and to work on getting viral load processed and built into the sensors. For that, I would like to acknowledge PI Kevin Daniels, Serrano, and 2 other people. I forgot to put them on here. Michael Pedowitz, he worked with me in the lab, and John Herbosek, he helped me with the etching process. Thank you.